Okay, so continuing with this chapter about fields, last time we saw how do we find the equation of propagation of electromagnetic waves, starting from the relativity or in space-time when we're considering the fourth dimension of time. Okay, so actually we are building a theory of motion of particles, and always when we say motion of particles, we always go to the principle of least action. There is no other way to determine the equations of motion or the theory of motion of any particle. The only way is to use the principle of least action. The least action, so it's related to an action, which is a sum or an integral along a trajectory. The trajectory, of course, is divided into segments, and this action should be invariant in all inertial frames. So it's an invariant by the Lorentz transformation. So whenever you have a particle that is going along a certain trajectory from point A to B, you can take this trajectory and divide it into small segments, into differential segments, according to space and time. And of course, the invariant in any of these intervals would be the proper time. So it's the simplest, most direct invariant in space-time, which is the proper time as in t squared minus x squared. So we have to create equations with invariant quantities, using invariant quantities in order to have a total action, an action which is the sum of all small actions. In order to have this action an invariant of space-time, so it should be done by a sum of invariant quantities. So they should have a Lorentz transformation. They should go, or if you go from one frame to another frame through the Lorentz transformation, this should be invariant. The quantity along with its differential quantities. So if you have a quantity phi that is invariant, also the differentials of phi, the partial derivatives of phi should also be invariant by the Lorentz transformation. Okay, so we are working with fields. The simplest way to study fields is to use scalar fields. In this course, I will be using a lot of scalar fields. Okay, we also have vector fields, but for simplicity and because it's easier to see it and to understand it, I will use, for now, I will use scalar fields. Okay, a scalar should be invariant. A scalar is invariant. If it is a scalar, it is invariant. So when you have a frame R, let's say X and T, and you have a frame R prime, X prime, and T prime, if R prime is moving at a certain speed V, you know that the axes X prime and T prime would be deviated from X and T by a certain angle theta, which is the same here and here. So a scalar field is an invariant field. So phi in this on first frame would be equal to phi prime in the second frame, X prime, T prime, if they are both inertial frames. So the coordinates and the differential quantities of these coordinates are invariant, or they are transformed by the Lorentz transformation. They have a Lorentz transformation for each quantity and for each differential quantity of the same quantity. Okay, let us suppose a certain 4 vector A. It's a 4-vector, so it has 4 coordinates, a time coordinate and 3 space coordinates. They all have a Lorentz transformation, so A0 prime should be equal to A0 minus VA1 over the radical of 1 minus V squared. A1 prime is equal to A1 minus VA0 over the radical of 1 V squared. Your radical, simple Lorentz transformation as you know it. And for coordinates y and z, they stay the same. A2 prime is equal to A2, A3 prime is equal to A3. So our coordinates, the coordinates of this 4-vector A mu, as in any addition of coordinates in space-time, mu goes from 0 to 3. And these coordinates are, of course, function of t and x. So you have a 4-vector. From this 4-vector, from these coordinates of the 4-vector, you can construct, you can get a scalar quantity. And the most direct scalar quantities that you can use starting from a 4-vector is simply go to the proper time of this 4-vector, which is the zeros coordinates squared minus the space coordinates squared. So it's A0 squared minus A1 squared minus A2 squared minus A3 squared. It is an invariant by the Lorentz transformation because it follows the same form, the same pattern of the proper time. It is the proper time. It's the time coordinates squared minus the space coordinates squared. So it is a proper time, so it is invariant by Lorentz. Okay, the derivatives of a scalar, of course, with respect to the 4 dimensions of space-time, they form a 4-vector. So when you calculate the partial derivatives of phi with respect to x mu, it means with respect to t, x, y, and z, the 4 derivatives, the 4 partial derivatives of phi, of the scalar phi, with respect to each one of the 4 dimensions, these 4 quantities will also form a 4-vector. So you will get a 4-vector with 4 coordinates that are the partial derivatives of phi, the scalar phi, with respect to each one of the 4 dimensions. So we need to have an invariant action. If the action is invariant, and you know that the action is the integral of a Lagrangian times dt, so our Lagrangian, the Lagrangian itself should be invariant. Otherwise, the action would not be invariant. So in order to have an invariant action, the Lagrangian itself should be invariant. So L, the Lagrangian L, is invariant. So it is a scalar. If phi is a scalar, so L is a scalar. So all the functions of phi are also scalar. So instead of phi, you can have phi squared, phi cubed, cosine phi, tangent phi. Any function of phi should also be a scalar because phi itself is a scalar field. So all these quantities, all these scalar quantities are candidates to be part of the Lagrangian. So our Lagrangian should be constructed by invariant quantities, and all of these quantities, phi, the derivatives of phi, the functions of phi, are all candidates to be part of this Lagrangian. So we make the derivatives in a way to have scalars. The sum of the derivatives is a scalar, so it is invariant. So del phi over del x mu, the 4 derivatives. So first we begin with respect to t. It's del phi over del t squared with 1 over c squared. You add the 1 over c squared because in the case where c is not equal to 1, or if you are working with an electromagnetic wave traveling not in vacuum, so you replace C by V. So here we need to keep our 1 over C squared. So the derivatives is 1 over C squared del phi over del T squared minus, we keep always the same form of a proper time. So it's the time squared minus the space squared. So minus the partial derivative of phi with respect to x squared minus partial derivative of phi with respect to y squared with respect to z squared, etc. It is an invariant. It has the same form of a proper time. It's a 0's coordinates squared minus 3 space coordinates squared. So the scalar, this quantity is a scalar. It is an invariant. And with scalars, with any scalar, you can multiply the scalar by another scalar, and it stays a scalar. So any scalar that is multiplied by another scalar will be a scalar. So if you take this quantity, the sum of partial derivatives squared, and you put it inside of these brackets, and you multiply it by any function, any scalar function of phi, it would stay invariant. So this f of phi is any function of phi, any scalar function of phi, multiplied by this scalar quantity. The result would also be a scalar. It's a scalar product of two scalar quantities that stays scalar. So we have this scalar quantity because we need to introduce a function of phi. We need to be related to the field phi. So by convention, it's just a convention. We add a 1/2. So we multiply by another 1/2. It's 1/2 this quantity times the function f of phi. Why do we add this 1 over 2? It's just because we need to find Newton equations when we go to non-relativistic approximation. So when you calculate your approximation at low velocities or at low speeds, when you need to find the Newtonian approximation, you should find Newton equations. So in order to find Newton equations at low speeds, we just add this 1 over 1/2. It doesn't have any meaning in physics. It doesn't change anything in the physical meaning of the equation. It's not related to physics, just a mathematical quantity that we add in order to find Newton equations at low speeds. So our Lagrangian L should be formed by these quantities. I mean, the quantity here, the invariant quantity times a function of phi. So it's half the invariant quantity 1 over c squared del phi over del t squared minus del phi over del x squared minus del phi over del y squared minus del phi over del z squared. It's the same bracket in the previous slide times the function of phi. We choose to put it in the form of half mu squared phi squared, which will represent a potential energy, and later on in this session we will see why it is considered as a potential energy. So potential energies, they always take the form of a quantity times phi squared, or as in if you compare it to non-relativistic potential energies, it's like the elastic potential energy, the potential energy of a spring, which is half kx squared, for example. Your field is x. So x is half K x squared K, the stiffness of your string K now is designed by the quantity mu squared. We always use mu in space-time. So never mind about non-relativistic approximation. It's a form of a potential energy that is we put it in the form of half mu squared phi squared. It should be a function of phi. It is a function of phi or phi squared. So we put it in this form, and we will see later how to get it into a potential energy. Okay, so this will give us the wave equation that you already know, which is 1 over c squared del squared phi over del t squared minus the partial derivative with respect minus the second derivative. Here we are making the derivative of L with respect to each of the variables. So the sum of all partial derivatives of L. Here we are calculating dL over del x mu according to the Euler-Lagrange equation. Here we are applying the Euler-Lagrange quantity. So it's we begin with the derivative of L with respect to t. It's 1 over c squared. The derivative of del phi over del t squared is 2 del over del t of del phi over del t. So it's the second derivative of phi with respect to t. So it's del squared phi over del t squared. And the 2 goes with the 1/2, and you get 1. So it's 1 over c squared, the second derivative of phi with respect to t. So it's del squared phi over del t squared minus. Now we make the derivative with respect to x. So we are deriving this quantity. It's minus del over del x of this quantity. So it's 2 times 1/2, you get 1. So it's the second derivative del squared phi over del x squared, etc. minus del phi squared over del squared phi over del y squared minus del squared phi over del z squared, which is equal to del L over del phi, or minus del L over del phi, which is equal to 0. So it's del L over del phi, it's 2 times 1/2 of mu squared phi. So it's mu squared phi, which is equal to 0. This is the Euler-Lagrange equation applied to this L. Okay, so we get this quantity, which is the wave equation that derives from L according to Euler-Lagrange. Okay, so it is a simple field theory with only a linear equation, which is a function of phi. There is no phi squared, no phi cubed, no phi to the power anything. It's just phi. It's a linear equation that is a function of phi. And here I will keep repeating this. Never confuse between the second derivative here, del squared phi over del t squared, or any second derivative. Don't ever confuse it with the first derivative squared. Here, del phi over del t squared is the first derivative that is squared, and here it's the second derivative. It's del squared phi over del t squared. It's the second derivative. Here, nothing is squared. It's the second derivative. Here, it's the first derivative squared. This one is the second derivative. Never confuse between these two quantities. Okay, so what is the relation? We know now about Lagrangians. We know how to to derive the wave equation from our scalar Lagrangian, etc. So now we need to find the relation between particles and fields. So how would particles interact with fields, especially here in our case, scalar fields? And when you say interaction, so it is a part of the total action. This interaction between a particle and a field, and the field, is a part of the total action. It's an interaction that should be part of the total action. So if it is a part of the total action, so there is a Lagrangian that corresponds to this interaction. So we have our Lagrangian, the Lagrangian of the field, and we should add to this Lagrangian as another quantity corresponding to this new interaction between the particle and the field. So this interaction is related to some Lagrangian that we should add to the total Lagrangian. It would be the Lagrangian of this interaction, which is a part of the total action. So if you have a mobile particle in a known field phi, which is of course a function of t and x. X here is x, y, and z. X represents the 3D space. So your field phi in space-time is a function of t and x. So the particle would interact or could interact with the field. It's like when you put a charged particle in an electromagnetic field. If you put an electron, a mobile electron, into an electromagnetic field, you know that the electron, because it is charged, will be accelerated by the electric field, and plus the magnetic field will make its trajectory as a circular trajectory, as a curved trajectory. You know this from the courses of electrostatics or electromagnetic. When you put an electron into an electromagnetic field, you have two forces. The electric field will accelerate, will linearly accelerate the electron, and the magnetic field will turn the trajectory into a circular trajectory. So here you have an interaction of this particle, which is the electron, with the electromagnetic field. So we have a possibility to use invariance in order to get this Lagrangian. And the invariant is always the proper time, d tau or delta tau or t squared minus x squared, whatever form of the proper time. So we should always use the proper time, which is the shortest distance in space-time between 2 points, which is invariant in all inertial frames. So we should always use this proper time. So this part of the Lagrangian, or the action, here I am putting an integral, so it's a part of the action. We always have the form of minus m, which is the Newtonian regular mass, which is the only mass that is called a mass. As we said it last time, m is the mass that is measured at rest. It's the same as the Newtonian mass, the same mass everywhere. And the minus sign, you know that it is used to find the Newton equations when we make the approximation at low speeds. So this partial, or this part of the action is minus m integral of d tau. So that corresponds here, because we have an integral, it's an action, not a Lagrangian. But anyway, you can even call it a Lagrangian if you want. Minus m d tau is the radical of dt squared minus dx squared. So it's minus m integral. If you put the dt outside, it's the radical of 1 minus v squared dt. We've done this many times, so you know how to do. Okay, So this particle will interact with the field. So we will let it interact with the field. So we should add another quantity to this Lagrangian. This is the Lagrangian of the field. Now we should add a Lagrangian concerning this interaction, the interaction of the particle with the field. And this quantity that we should add to the Lagrangian should also be invariant. We only work with invariant quantities. If you are a physicist, if you are working physics, if you are doing physics, you always need to have invariant quantities. Non-invariant quantities are not related to physics. It's maybe, I don't know what, anything other than physics. So this quantity should be an invariant by the Lorentz transformation. So in this case, because we are using a scalar Lagrangian and a scalar field, so the only quantities we could use are scalar quantities. So this Lagrangian should be a scalar. One thing we could use, which should be a function of phi, of course, because it is related to the field. So we have minus m d tau, which is the initial Lagrangian of the field, plus we add something related to that should be a function of phi. So let's say it is phi d tau, or any function of phi. It could be phi squared, it could be phi cubed, any function of phi times the proper time, which is the invariant, our invariant, d tau. So phi is a scalar, d tau is invariant, so scalar times an invariant is an invariant, so we are here working with invariants. And this is what we should do anyway. Okay, so it could be phi, it could be 2 phi, it could be 1/2 phi, it could be a phi squared, any function of phi, any scalar function of phi d tau. So now our Lagrangian or our action is the integral of minus m plus phi if you put the d tau as a common factor. So it's minus m plus phi times d tau, which is the radical of 1 minus v squared dt. Okay, so if you compare it to this form of the Lagrangian, so we have this minus m that represents the mass, or m, it is the mass. So we have the Lagrangian formed by minus m times the radical of d tau. So here minus m becomes minus m plus phi. So if you multiply by a minus here, we should have a minus. So it's like it is a particle, a free particle in a scalar field that has a mass of m minus phi. So it's like you have a field and a free particle inside this field with a mass m minus phi. So instead of have a mass m, it has a mass m minus phi. It could be m plus phi, because phi could be negative. So m minus phi or m plus phi. So what do we mean by this quantity is that the field could shift the mass of a particle. So this is an example of how a scalar field could shift the mass of a particle, which is the Higgs field. So if you are a physicist, you should know, or maybe you don't know about, but at least you have heard about Higgs fields. The Higgs field will explain or will try to explain how a mass or how a particle could acquire its mass. So when we talk masses, how do we get the mass? Why do a particle have a mass? Why a particle have masses, have inertia in space or in space-time? This is explained by Higgs by the theory of Higgs fields, which is also related to the Higgs boson, the famous Higgs boson, the famous particle that is exchanged when field and particles interact. We call it the Higgs boson, that is related directly to the Higgs field. So how masses are created by this interaction between the field and the particle, which will create the mass. Now, for now, in this course, I will not go into further details about the Higgs field and the Higgs boson, because it's not a part of this course. But if you are curious enough, if you have enough scientific curiosity, you can make a small research about the Higgs field and the Higgs boson, and you can see it. There are a lot of videos about it on YouTube or on the sites dealing with physics or theories of physics, etc. Okay, it's not a part of this course, but I recommend you to have to make this research and to be curious enough to search for new things in physics. So here the field is shifting the mass, so maybe it's an extreme case. If a mass was initially zero without the field, it could become a non-zero mass in a field. Maybe it's an extreme case, but the possibility is here. So it's a non-zero probability. Okay, fields. So when we have fields, when we have a Lagrangian, a field, when a Lagrangian and an action, so we can use the Euler-Lagrange equation to find the equations of motion. So we are doing this whole theory to determine the equations of motion of particles inside fields. So let's calculate the Euler-Lagrange equation to or related to the field of this particle and the interaction of the particle and the field. So we can calculate the partial derivative of L with respect to x dot, and you know that x dot is del x over del t, etc. And with respect to all the dimensions. So we have 4 equations. So here del L over del x dot is m minus 5. So we are using this L. So it's m minus 5 x dot over the radical of 1 minus x dot squared or v squared, whatever. So this del L over del x dot is the definition of momentum. So it is the momentum, the linear momentum. Well, in space-time, we don't say linear, but it's equivalent to the Newtonian linear momentum. So this is the momentum of a mass m minus 5. So our mass now is m minus 5. So this quantity is the momentum of the mass m minus 5. Okay, so let's put this aside. Let's calculate the Euler-Lagrange equation. We need d over dt of del L over del x dot, which is d over dt of this quantity. That should be equal to del L over del x according to Euler-Lagrange. So del L over del x is minus del phi over del x times the radical of 1 minus x dot squared, because m minus phi doesn't have an x here. So m minus phi is a constant according to x. So the derivative of this L with respect to x is only the derivative of phi. So m is not related to phi. So we have only the derivative of phi. So it's m, so it's minus del phi over del x, radical of 1 minus x squared. So you should repeat these calculations by yourselves in order to fully follow the mathematics of this. Okay, so it's here we take this equality here, so it's m minus phi. So it's like you are doing the derivative of u times v. It's u prime v plus v prime u, etc. Any regular derivative of the product of two quantities. So d over dt of this quantity, it's m minus phi d over dt of the second quantity x prime of the radical of 1 minus x squared plus the derivative of the first quantity, it's minus d phi over dt or minus phi dot times the second quantity x dot over radical 1 minus x dot squared. So it's derivative of uv, it's u prime v plus v prime u, which is equal to del L over del X minus del phi over del X radical of 1 minus X dot squared. Okay, to simplify the equation and not to write all the derivatives, we will suppose, just for simplicity, that the field depends only on X. Okay, so it's the same equation, but only along x in space. Of course, we always have the top. So phi dot is del phi over del x times x dot, the differential of phi dot. Sorry. It's del phi over del x times x dot. So here the equation would become m minus phi d over dt x dot radical of 1 minus x dot squared minus phi dot. We replace phi dot by this quantity. It's minus del phi over del x dot times x dot. It's x dot squared over the radical of 1 minus x dot squared, which is equal to minus del phi over del x radical of 1 minus x dot squared. So we're just replacing phi dot by this quantity. Okay. So this is the result of the Euler-Lagrange equation according to the Lagrangian that takes into consideration the interaction of the particle with the field. Okay, so now we have a field, we have a particle. So if the field has an effect on the particle, we can easily suppose that the particle has an effect on the field. This is the simple principle of interaction. If A affects B, then B will react and B will affect A. So the same case of the charged particle in electromagnetic field. The field will change the motion of the particle, it will accelerate it, it will change the trajectory, etc. And the particle itself will also change the field. I will consider the same example of an electron in an electromagnetic field. So when you put an electron into a magnetic field, the electron will be accelerated and will have a circular trajectory because it is inside this electromagnetic field. But when the electron circulates around this circular trajectory, it will create its own field. So it will add a field to the initial field. So here, the particle also affects the field or changes the field. So field changes the motion of the particle, and the motion of the particle will change also the field, such as an electron circulating in an electromagnetic field. So you know this from the electromagnetic courses, You saw this in the first year in the course of electrostatics, or in the second year with electrodynamics, etc. You've seen this several times. So when electrons are subjected to a field, the field will change the motion, and the motion of electron will also create a field. So it's an interaction. If we have a field phi, a scalar field phi that is a function of t and x as always, the Lagrangian of the particle would be, you know it, it's minus m, a radical of 1 minus x dot squared. So it corresponds to a quantity that is the sum of actions. So the total action will correspond to a quantity that is the sum of actions along the trajectory. So if you have the trajectory of your particle, your electron, your proton, your any particle, you can divide this trajectory into small intervals, into differential intervals. So the action of this particle would be the integral of L of the particle times dt. So it is the integral of minus m radical of 1 minus x dot squared dt. And if you take the field into consideration, so you should add a phi to the m. So here you can take m plus phi or m minus phi, as we saw it in the shifting of the mass inside a field. Let's take m plus phi. So here we add the field to the mass. It's the integral of minus m plus phi radical of 1 minus x dot squared dt, because the Lagrangian that we add is plus phi d tau. So it's plus phi d tau. So it's you put the d tau, the proper time, as a common factor. So we have minus m plus phi radical of 1 minus x dot squared dt. Okay, so if we take this equation, this action here, and we calculate the approximation as a non-relativistic approximation, so the Newtonian case, which is calculated at low speeds, and always considering a motion along x, so we will not complicate too much the equations. So it's the integral of, here we should add the c squared, because we need a c that is different from 1 here at in order to calculate the approximation. So you know that Lagrangians have the same dimension of energies, because you know classical Lagrangian is the kinetic energy minus the potential energy. So all Lagrangians, Newtonian or relativistic, the Lagrangians have the dimension of energy. So m is really mc squared to be of the same dimension of energy. Plus phi, okay, plus phi, when we say here in this equation plus phi, we mean a function of phi that could be 1 and that could be different from 1. So let's say it's g of phi. G could be 1, and in a lot of cases it is 1, but in some cases it's not 1. So instead of putting only plus phi or plus 1 phi, let's say it's plus g of phi. Okay, it could be 1, but let's say g of phi times the radical of 1 minus x dot squared e over c squared. Here we are using this c times dt. So g here is called the coupling constant between field and particle, between the field and the particle. It is a coupling constant. We call it the coupling constant. Okay, so here it is the integral of minus mc squared plus g of phi. If you are working at low speeds, So your radical here would be a series of, so if you replace it here, a radical of 1 minus x dot squared over c squared, it's 1 minus x dot squared over c squared to the power 1/2. And here is a term that tends to 0, so it's 1 minus half x dot squared over c squared. So we have a 1/2 here, etc. So the radical is 1 minus x dot squared over 2c squared times dt. So here inside the radical is the Lagrangian. So the Lagrangian is minus mc squared. Here we develop these two brackets. So it's minus mc squared plus mx dot squared over 2c squared times c squared. So you simplify by a c squared minus g phi minus and minus plus g phi x dot squared over 2c squared. So here is a quantity that is divided by 2c squared, so it tends to 0 if the velocity is low, and mc squared is just the rest energy that is not taken into account in the Newtonian cases. In fact, it is a scalar quantity. It's just a number. You can add it, you can remove it, you can do whatever you like with it. You can remove it because in Newtonian approximation, mc squared is the rest energy, and we don't consider the rest energy in Newtonian cases. So, and it is a number here, so you can remove it in a Newtonian case, just in a Newtonian case, not in a relativistic case. So your Lagrangian would be half mx dot squared minus g of phi. Okay, so here you can see it in this approximation, in this Newtonian approximation, because you know that this quantity corresponds to the kinetic energy minus the potential energy. Here the kinetic energy is half mx dot squared, and you know x dot squared is v squared in a classical case. So this is the kinetic energy. And here, so g of phi should be the potential energy. So now you understand how potential energies are obtained. You know why do we have potential energies in our daily life or our Newtonian physics. Because in classical mechanics, there is no explanation, real explanation of why do we have a potential energy. We know that we have a potential energy. We call it a potential energy because it has the potential to be released into kinetic energy. You know this from the first year, from the course of classical mechanics. So the definition of potential energy is an energy that is stored in the system. So it's a stored energy that has the potential to be transformed or to be released into kinetic energy. This is the only explanation given by classical mechanics. So here now, when we calculate this quantity through the space-time, through relativity, you know that by approximation into a Newtonian case, how did we get this this potential energy? So now you know how to get potential energy, or from where do we have this potential energy. So here is the effect of the field over the particle, what we call in a Newtonian case the potential energy. Okay, so now let's find the effect of the particle on the field, because we already know the effect of the field on the particle. Now we need to see the effect of the particle on the field. So you know that the total action is the sum of two actions, the action of the field on the particle plus the action of the particle on the field. So the total action is the sum of both actions. In order to calculate this, we will consider a region of space-time containing a field. So here in the drawing here, it's a region of space-time. So just remember that X represents the 3D space. So here X is X, Y, and Z. So we will choose a region in space-time containing a scalar field phi, and we have a particle that is moving in this field, shown here by this blue trajectory. So the particle is moving from this point to this point inside the field along this blue trajectory. The blue trajectory, of course, represents the trajectory of minimal action, or the least action. So we have an action that should be an extremum or minimum or maximum. I always use the term minimum. So the action should be minimum. So the principle of least action. The action of the field that was found previously on the previous slides, it is the integral of L dx mu, which is the integral of half 1 over c squared del x over del t squared minus del phi over del x squared dx mu. And here you have also del phi over del y squared, etc. We are considering motion along x here. So not to complicate the equation. So we have the field found previously the action of the field. Now we need the action or the Lagrangian of the particle. We should add something to this Lagrangian to take into consideration the particle. I will consider the most simple case of a particle at rest at x equals 0. So in this case, x dot would be equal 0. So the contribution of the particle to the Lagrangian is g phi, what we saw previously as g phi or minus g phi. It would be minus g phi at 0t, because it's on x equals 0 times dt. This partial action, this part of the action should be added to this action, to the total action. So the total action here, but here, look at these equations. So we should add this action to this action in order to have the total action. But let's look at the integrals. We have an integral over dx mu. It means over dt, dx, dy, dz. And here we have an integral that is over dt. So mathematically speaking, these two integrals are not compatible. 1 over dx mu, 1 over dt. So mathematically speaking, we have an integral over dx mu and an integral over dt. They are not compatible. So how do we get to add these two integrals? We have only one way to do it, is to use the delta function of Dirac, which is this function. Okay, don't be afraid of the delta function of Dirac. It is not requested for this course, so don't be afraid of this equation. It's just a mathematical function, a mathematical equation, a function that we use in this case. So you're not responsible of this function. the function of Dirac, the delta function of Dirac, is represented here. It is a function that is equal to 0 everywhere except for x equals 0. So only for x equals 0, this function has a large value, a very high value, a very large value for x equals 0. And for all other x's, for all other values of x, it is equal to 0. I will repeat it. This function is equal to 0 everywhere, except for one point that is x equals 0. So only for x equals 0, it has a large value. And for all other values of x, it is equal to 0. This is what we call the delta function of Dirac. The delta function of Dirac. Don't be afraid of the equation. It's a simple equation. Just remember it is a function that is 0 for all space-time, except for x equals 0, it has a large value. So in this case, minus g phi of 0t is the integral. Is the integral of minus g phi of x by delta Dirac of x times d3x, or delta 3 of x here. Or you can write it in one dimension, integral of phi x delta x dx, because delta 3 of phi is delta x, delta y, delta z. It is non-zero if all three are non-zero. So delta x, delta y, delta z should be non-zero. For x equals 0, for y equals 0, for z equals 0. Okay, it's the delta function of Dirac. It has only a non-zero value at the point 0. So minus g phi of 0t is the integral of phi of x, y, and z, delta x, delta y, delta z times dx, dy, dz. Don't consider it as a too complicated equation. It's just a representation from this delta, from the use of this delta function of Dirac. Okay, so the action is the sum. The action is the sum of both integrals. So it's the integral of 1/2 1 over c squared del phi over del t squared minus del phi over del x squared dx mu minus the new delta function of Dirac minus g delta 3 of x phi of x dx mu. So we put dx mu as a common factor. You have this quantity that is 1/2 times 1 over c squared del phi over del t squared minus del phi over del x squared minus g delta 3 of x phi of x. So this quantity inside the integral is the total Lagrangian. And this part here, which is minus g delta 3 of x phi of x, is the part of the Lagrangian that corresponds to the effect of the particle on the field. Of course, it's the effect of the particle on the field. So this minus g delta 3 x phi of x is the effect of the contribution of the particle to the total Lagrangian and consequently to the total action, which is the integral. Okay, so now we have our Lagrangian. If you have a Lagrangian, you can put it in the Euler-Lagrange equation in order to have the equations of motion. So del over del t of del L, da over del of del phi over del t, which is del phi dot, as in a Lagrange equation, using this L. So it's 1 over c squared del second derivative. So the square with the 1/2 should be simplified. You get del squared of phi over del t squared, the second derivative, not a derivative squared. This is the second derivative of phi with respect to t minus the second derivative of phi with respect to x, with respect to y, with respect to z. And the other part of the Euler-Lagrange equation, which is del L over del phi. Okay, del L over del phi, here we have minus g delta 3 of x. These quantities are equal. So 1 over c squared del squared phi over del t squared minus del phi squared del squared phi over del x squared minus del squared over del y squared minus del squared over del z squared is equal to minus g delta 3 of x. So you see this is the same equation of propagation of electromagnetic waves except for this quantity. So at a certain point in space-time, which is for x equals 0, there is something that is different. So it's the same equation of propagation of space-time, except for a certain point in space-time where we have something that is different from the rest of the space-time. So if this particle is at rest and the field is dependent of time, just a case where a particle is at rest and a field that is independent of time, so del squared over del t squared of phi is 0. So you get del squared phi over del x squared plus del squared phi over del y squared plus del squared phi over del z squared, which is equal to g delta 3 of x. So here we are multiplying by a minus. So if you remember this quantity, the sum of the second derivatives, it is the Poisson equation of an electrostatic potential. You saw it in the course of electrostatics in your first year of physics. The sum of second derivatives, which is represented by this symbol, you used to call it the Laplace symbol or the Laplacian or whatever you call it. So this is the sum, the Poisson equation, the sum of the second derivatives of the field phi, which represents the electrostatic potential. Here, in this case, G delta 3 of x is the density of charges, is the density of charges in this field. So if you remember it from the course of electrostatics. So it is the potential, the electrostatic potential that is equal to the density of charges in the field. Okay, let's take another case. If the particle is in a position that is different from 0, let's not equal to 0, it's different from 0. Okay, it is different from 0. So for a particle that is at x different from 0, so this Poisson equation should be or would be equal to G delta 3 of not x minus a, because this quantity is only valid for the position x equals 0. So we replace x by x minus a if a is the position of the particle along x. So if the particle is x equals a, not 0. So if the particle is in motion and This is another case. So if the particle is in motion and the position is given by A, which is a function of t, so the Poisson equation is equal to G delta X minus A of t for each instant of time. But here you have to pay attention that when the particle is mobile, the field will not stay the same and will not be independent of time. It will become dependent of time. So we should add the minus 1 over c squared del squared phi over delta t squared del t squared minus the Laplacian squared or the Poisson equation squared of phi minus g delta x minus a of t. This is the equation of emission. Any emission of electromagnetic waves is described by this equation. The emission of electromagnetic radiation. So let's go back to our wave equation, which is 1/2 of 1 over c squared, first derivative squared minus the first derivative squared, etc., minus mu squared phi squared. Let's calculate the Euler Lagrange equation from this Lagrange, from this equation. So it's 1 over c squared del squared phi over del t squared, the second derivative, minus the second derivative with respect to x, with respect to y, with respect to z. That is equal to the partial derivative of L with respect to phi, which is here, minus mu squared phi. So we can put it in this form, 1 over c squared del squared phi over del t squared minus del squared phi over del x squared, etc., plus mu squared of phi is equal to 0. This equation is called the Klein-Gordon equation. The Klein-Gordon equation is the relativistic form of the Schrodinger equation, known as the Klein-Gordon equation. In fact, Klein and Gordon found this equation before Schrodinger, but they found it in this relativistic form in 4 dimensions in space-time. So Schrodinger came and he took this equation, he put it in a non-relativistic form, which is now known as the Schrodinger equation. And everyone now call it the Schrodinger equation in the non-relativistic form. So everyone call it the Schrodinger equation. But in reality, the real equation is this 4-dimensional equation. This is the real equation of quantum mechanics. The Klein-Gordon equation, the real equation of quantum mechanics. The Schrodinger equation is the non-relativistic form of the same Klein-Gordon equation. I don't know why they call it the Schrodinger equation, but this is the real space-time 4-dimensional equation of quantum mechanics. And the solution to this equation is a sum of plane waves. So if you have a plane wave defined by a phi, which is exponential of minus e omega t, which is the pulse or the angular frequency, 2 pi times f, it's e minus I omega t times e to the power I kx of x plus ky of y plus kz of z. K is the wave vector